Okay. All right. So that should be recording, hopefully. All right. Hopefully it doesn't stop. Okay. Next, we'll talk about replacement lecture soon lah. I think that one maybe have to do on Saturday. All right. But maybe later lah. Some of you doing women competition, is it? What Saturday do you use? Week 8 Week 7. Next week Next week Maybe week 8 like that lah. Okay? Week 8 also not good lah. We'll talk about that later lah. Alright? What's more pressing quiet please. Next Friday holiday because Merdeka. Alright? So next Friday still I don't want to delay the replacement. Alright? So when are you guys free? A bit pointless to take the Friday off and then come back on Saturday and do it, isn't it? Alright? So my plan is to do it early. Alright? Do early. So when you guys can do early? On the day. So I propose maybe, so this one is next Friday, week 6 Friday. Next week's week 6. Alright, so maybe Monday. What time? 4 to 7, okay? And Tuesday is a tutorial. So those who are doing on Wednesday, then no change. You can still come on Wednesday. Those who prefer to come on Wednesday and can come on Wednesday, you are most welcome to come on Wednesday. But those whose classes are on Friday morning and Friday afternoon, that has to be rescheduled. I propose to be done early next week. All right. Wednesday, 3 to 6 on which day? On which day? Monday, 3 to 6, okay? Alright? If you have lecture on that day, oh yeah, I have a lecture also. Alright? But if you cannot make it on that day, I put 3 here, but I run 2 of them. So which 2 can everyone make it? Monday 4 to 7, Tuesday? So Monday you can, Tuesday also cannot. So Monday and Wednesday? What is that? Can you come on Wednesday? 1 to 4. Alright, then it's okay, I will switch out. Alright. So any besides him, anyone has any problem or not? I think Tuesday is no good. So Tuesday no good. Can anyone make it or not? And then the other one be Wednesday 1 to 4. Okay, so you want Tuesday or Wednesday? You can only come on Monday. So if I put Monday and Tuesday, who cannot come? Only 2 of you? So if next week's classes are Monday, Tuesday and Wednesday, who cannot come? All is cannot come. Why? Which one, Flash? What time? Next week. Wednesday. Wednesday what time? 4 to 7. So, which day can I drop off? Huh? Tuesday. So, like this, who cannot come? Huh? Who cannot? Only you only. Then, what time you have class after? But they got problem. What day can you come? Only can come on Tuesday. Huh? 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 Can we come on Tuesday? Alright? You need to all. Huh? Wednesday. Wednesday fine. Monday is fine. So, but some people need Tuesday. Okay. Maybe send my tutor. Ask him to do it. Okay, so who's coming on Monday? Alright, Tuesday? Not many as well. Wednesday? What? Wednesday, what? 4 to 7. Huh? You need some, those Wednesday, this Wednesday, you cannot come on the other slots. Huh? Okay. So looks like I have to run extra class. Huh? Do I need to have this one? Take off this one. Huh? What? What? You go that one. If I close this one, everybody can come or not? Alright. Huh? Yeah. Okay. So next year I'll try to book the room now. There existing is this one, only this one. Yeah. Okay, quiet please. I'll try to book the room and then we'll see whether I can get or not. Okay? Yeah, if not, it'll be Saturday already. Okay? Monday, Tuesday. Alright. Okay, quiet please. Alright. Okay, so so this one's okay. The next one, following our schedule, if you haven't seen, okay, the lab report, the first one is due on week 7. Alright, week 7 Monday. Then after that, week 9 and so on. Alright, 7, 9, I think 10 and 12 or something like that. Alright, so they're spaced out over the next half of the semester. Okay, so I better start you guys off on the impact jet first. Alright, that one's fairly easy, okay, so it's due here. Alright, so quiet please, settle down. Okay, so the lab report on week, settle down please. The lab report due on week 7. Alright, Monday. Okay, so so you done all your measurements. Okay, so to estimate the force, don't try to copy down. This will be available on the Moodle. Okay, so you listen to me, let me explain. So some of you, if you don't know which experiment I'm talking about, that's the one with the water shooting up one. Alright, there was a cup and there was a plate. You measured the force. Some of you were putting weights on top, then your force was easy lah, mg only. Alright, some of you had that funny thing like a lever, right? Like a lever with a weight on it. Remember or not? Alright, and then you measure distance. Okay, if you did that, then I did analysis for you here. Okay, all you have to do is write one moment equation without the water, one moment equation with the water on, with the jet shooting up. With the jet shooting up, the distance of this is offset by a distance d. Okay or not? That's the one you measured. Alright, you measured d. Okay? Alright, so you take this minus this, you get this. Alright? The only distance you need to know is the distance from the pivot to the jet is 150 mm, that's provided. And the weight of the mass is 600 grams. And what else? Huh? That's all you need to know. Okay? The spring force, all that will cancel out because it's initially at equilibrium and finally at equilibrium, so they all subtract away. Okay? The distance y from the pivot to the zero here also actually doesn't matter. Okay? So that's all you need to know to calculate the jet. It'll be just some constant here multiplied by the distance you measured in mm. Is that okay? Yeah? Okay? Next. Alright? You need to plot. Alright? For the analysis part, you need to plot the graph that look like this. Alright? The measured forces for the cup and for the plate, and the theoretical forces for the cup and for the plate. Alright? I forgot right here, theoretical. Alright? As a function of flow rate. Okay or not? Alright? Again, you don't need to copy down. You can download and look at it. Alright? More important, you listen to me. Alright? But I think more people like to copy and then figure out later. Okay? Alright? So this is what you need to plot. You can plot one graph or two graphs. Up to you. Okay? Alright. So finally, this one is quite straightforward. The volumetric flow rate is the volume over time. You measure the volume, how many liters, you measure the time, and here you should convert it to meter cube per second. Okay? Alright? So you convert your liter. The force is either mg, which you put on top, or the one that you use, the TQ1, the formula that I just gave earlier. Alright? TQ1 is the one with the lever. Lotus one is the one with the weights you put directly on top. Alright, the velocity of the jet is the volumetric flow rate. Alright, the volumetric flow rate divided by area of the jet. Alright, the area of the jet, for those doing the TQ, alright, the one with the lever arm, is 10 mm. The one doing the, what is 7 point? The Lotus, alright, the one with the weights on top is 7.7 mm. Okay, after that, this is your predicted force for the plate. Alright, I put the formula straight here. You can work it out. You draw the control volume, you draw it out. It should be rho, volumetric flow rate, Vjet. And this one, 2 rho V dot Vjet. Alright, please show this. Please show. Okay, that's your exercise. I'm not going to show you. Alright, I did similar problems already. Okay, any questions so far? Okay, so remember your report professionally presented, maximum six pages, is it? Okay, maximum 6 pages. Don't fill up tick like that. All right, and if you want to add a bit more value to your report, okay, one suggestion, all right, which I see a lot is people just list down what they think the errors is this error, that error, that, or and so on. Okay, so add value. If you want to add value, there are a lot of ways. All right, but this is one suggestion now. Maybe you should relate errors to the observation. Okay, so if your observation is under predicting, all right, your measurements are under predicting or whatever, try to see where the source of error is and why you think this is overestimate, that underestimate, discuss that and that how it relates to over prediction, under prediction, or something like that. All right. So rather than just listing out the errors, that's most likely where they come from, but not having, not showing a clear understanding of why this, if you do this or this, if this is the problem, this is what the outcome and so on. All right, so that could add value. Those who want, you can come and discuss it with me later if you want to do that. Okay, this one is for those who want to add value. Right, add value means the marks more than 7.5 one. Okay, out of 10. Okay, any questions? Okay, all right, don't panic. Now it's only week 5. Still got week 6. All right, week 6. Friday got holiday. It's a group report. All right, so if 4 of you, each of you do a little bit. All right, it's not that much to. Okay, all right. 4.5%. Any questions? All right. So that one's done. Okay. All right. So where we left off. All right, Bernoulli. Okay. So we did Bernoulli. What is it? P on rho G plus V squared on 2G plus H equals constant on streamline on a. All right, it's constant along a streamline. The somebody stole the fluff here. All right, it's constant along a streamline. Assuming steady state, no losses. All right, irrotational, which also means no losses. Rotational means the fluid does not rotate, does not spin into eddies, does not, all right, away from boundary layers. And wakes. Okay, so away from boundary layers and wakes, then you get all that. Then you it's a reasonably good assumption. Steady state, no losses, rotational, and so on. Okay. You might also, if you prefer, rho P plus rho V squared on 2 plus rho GH equals constant. Alright, whichever form you like, it's the same. Alright, and we did momentum. What is that? For the rho V vector dv integral d on dt plus integral rho v vector dot n multiplied by the v vector dA, all right, equals sum of forces. All right, that's the painful way of writing it. The simplified way is m dot out, v out, minus m dot in, v in, is equal to sum of forces. All right, this one normally we have pressure, we have viscous, we have pressure, viscous, gravity, and we have any external forces. All right, so we've done both of that. Again, this one, steady state, constant velocity, constant v. All right. Okay, so that's the complicated one, and that's the simple one. All right. So today, what we're going to do, we're going to combine the two. All right, because a lot of problems need a combined approach. Okay. Okay, so example. Previously, I was telling you the pressure in the pipe. Actually, you can, if you assume no losses, you can actually calculate the pressure in the pipe. So let's do that. Okay. So this is a complicated problem. All right, that involves both momentum. Okay, example. That both involves both Bernoulli and momentum. Let's see. Okay, let's say, okay, it might take about 20 minutes or so to do this problem. Never mind. Okay. Let's say we have a elbow, a contracting elbow. Okay, so I forgot. Also, we have mass conservation. Okay, but that one I'm sure. All right, we have a contracting elbow. Okay, so actually the pipe carries on lah. Alright, but I chose to choose, well, for this particular problem, I know the two locations here. I chose to use my control volume here. Alright, because I know information here and here. Okay, so my control volume like this. Okay, for here, this angle here, 30 degrees. Okay, so not only is it a contracting elbow, it's sloping up. Alright, not sloping up lah. Well, okay lah, sloping up. Okay, alright, what other complication can we add? Okay, we have streamline. So this is our streamline going through. This is our streamline going through. Okay, we are told here diameter equals 0.4 meters. Here diameter equals 0.15 meters. Okay, told here the velocity is maybe 3 meters per second. Here the velocity don't know. Alright, velocity 1, velocity 2. Here the pressure is equal to 400 kPa gauge. Alright, maybe more lah. 700 kPa gauge. Here P2 don't know. Alright, and here maybe mg maybe equals I don't know, 350 newtons. Okay, that's the weight of the pipe assembly. Weight of the pipe and the water inside. Okay, your question, find this can use for quiz question also. Find force required to hold elbow in place. Alright, this force can come from either external support or it can come from the two pipes that it is connected to. Alright, if it's come from the two pipes, then you have to make the pipe a bit stronger. Okay, if not the pipe might break, or you might have external support. Alright, normally piping system you can see around elbows there'll be external support also. Okay, if not, if especially at high pressure and carrying a lot of liquid, it might break. Okay, do I need anything else? I don't think so. Alright, in this case we can say H2 is approximately H1. Alright, although it goes up a little bit, you just ignore that. Alright, you want to ignore or you want to put some value? Ignore lah. Okay, or you can put, we put H2 maybe 1 meter, H1 equals 0 meter. Okay, above the datum. Alright, okay, so what's your first step? What can we find first? What's the easiest one to do first? No, don't do momentum first. Huh? Alright? Is the V2 can find or not? Alright? So, you find V2 first. Okay? So, normally with this type of question, the sequence, alright, is you normally use continuity to find any velocities that you don't know. Use Bernoulli to find any pressure that you don't know. Alright, you know both pressure and then use momentum, then only finally use momentum. Is that alright? That's the sequence, huh? Alright, write down in your shoe or somewhere. Alright? Okay, then preserve your shoe properly before you go to exam. Okay, it's being recorded now. Okay. Okay. All right, so can I say this one is steady state? All right, so m dot in must equal to m dot out, correct or not? All right, whatever goes in here must come out the other end. Okay, so therefore m dot in is what? Rho A in B in is equal to rho A out. Oh, this is water, by the way. Okay, all right, rho A out, B out. Okay or not? All right, so how to do? Okay, rho A in V in equals to rho A out V out. Okay, the rho can cancel out. A in is pi 0.4 square pi d squared over 4. V in is, what is V in? 3 is equal to A out pi 0.15 squared over 4 V out. Okay or not? Alright, so actually all this can cancel out. V out is equal to 0.4 squared over 0.15 squared multiplied by 3. What's the answer? How many meters per second? 21.3. So fast. Ooh. Okay. 10 meters per second is about 36 kilometers an hour. Never mind, this pipe really shooting out. Okay? Never mind, okay? It's strong. Okay? I don't know. It's really coming out 70 kilometers an hour. Okay? Alright, so second one, I told you use Bernoulli. Between 0.1 to 0.2. Alright, that's the standard procedure. P1 plus half rho V1 squared plus H1 is equal to rho G H1 is equal to P2 plus half rho V2 squared plus rho G H2. Okay or not? Alright, that's your Bernoulli equation. P1, again don't be sloppy. A lot of times I see people, they put 700, they forget to put the 1000. Alright? All the SI unit, so 700, 1000. Plus half, rho here is 998. P1 is what? 3. Plus rho G, H1 is 0, so it doesn't matter. Okay? Equals to P2 plus half rho 21.3 squared. Here 998. Plus rho 998 9.81 1 meter. Alright? So, what is P2? Is that okay or not? All follow or not? Alright? Okay, this is not spectator sport. You're supposed to calculate also. Okay, don't just rely on 1 or 2 in front here to do it. Alright? Any questions or not? Alright? Okay, so this is Pascal. Then finally, momentum. I'll wait 1 minute for a few. 467,000 or what? 467,600 Pascal. Is that okay, everyone? All right. Confirmation, independent, verified. Okay. Alright? So finally, okay? You all okay so far? Alright? So now this part is where it gets complicated. Alright, momentum, you need to do in the X and you need to do in the Y. Alright, let's do the X first. M dot out, V out, minus M dot in, V in, equals to sum of forces. Here we got F pressure, we got F viscous, F gravity, and F external. Alright, in the X direction, no gravity. Gravity is in the Y. Alright, I draw the coordinates up here. Okay, here X, here Y. Is that okay? Alright, so no gravity in the X. Alright, normally no viscous forces. M dot out is rho A out, V out. Okay, it's actually also rho A in, V in, it's the same. Alright, what is the X component going out? Cos 30, isn't it? Alright, so it's actually V out cos 30 degrees. Alright, not? Okay, because it's coming out at an angle of 30 degrees. Alright, so this is V out. Alright, it actually has two components, this way and this way. This one will be V out cos 30 degrees. This one will be V out sine 30 degrees. Okay or not? Alright. M dot out doesn't, as long as it goes out, it goes out. There's no direction, that one. So here, M dot out, as long as it goes out, it's out. Alright? The total that goes out. But the direction comes here. Is that okay? You only have to, only the X component carries momentum, carries X momentum out. Alright? Minus M dot in, rho A in, V in, multiply by V in. Okay? That one, nothing that special there. Is equal to F pressure P1 multiplied by A in. Alright? Here it's complicated. Minus P out, A out, multiplied by cos 30 degrees. Alright? Number one, why minus? Because, okay, we are looking at the pressure forces. Here, the pressure forces are drawn in green, like this. Okay? So they are in the positive X direction. That's why P in, A in. Here, the pressure forces are this way. Alright? So they are P out, A out, and we want the X component, which means P out, A out. Here, this one. Okay. So, sine 30 degrees. Okay. Sorry, cos 30 degrees. Alright? And it's negative because, alright, if this was the P out, A out, here is 30 degrees. Alright? We want this component and this component. Okay? So you look, this force, okay? Alright? This is P out, A out. Okay? It has a horizontal component and a vertical component. Alright? And this is 30 degrees. Okay? Can you see that the horizontal component is in the negative direction? Alright? Vertical component, positive or negative? Also negative. It's going down. Alright? Okay? So this is the pressure on the outlet side. Pressure on the inlet side is just in the X component. Alright? Remember, these are all gauge pressure, so the pressure outside the pipe, here, all zero. Okay or not? Alright, for our analysis, the pressure on, except for these two faces, pressure on all other surfaces is zero, relatively zero. Okay? So gauge pressure. If not, you have to worry about all that pressure. It gets funny. Okay. Plus F external. Yeah. Okay. So let's put some numbers in there. What is rho? 998. A out is what? Pi 1.5 squared. Okay. 0.15 squared over 4. B out is what? 21. What is it? 21.3. Alright. Multiply by 21.3 multiplied by cos 30 degrees. Minus in is 998 multiplied by pi 0.15 squared over 4. In is right, not mine. Pi 4.4 squared. What's the velocity coming? 3, is it? 3 multiplied by 3 equals to, what's the pressure here? 700,000. 700,000 multiplied by pi 0.15 squared over 4 minus pressure out. What's the pressure out? 467. 467, 600 multiplied by pi. You're wrong, huh? 0.4. A in, A out is pi 0.15 squared over 4 multiplied by cos 30. Alright, close brackets, plus F external. Okay, so F external, how many newtons? Okay? Everyone agree with what I did or not? Alright? What's your question? I can talk to you. But the others are still doing it. What's your question? Huh? Huh? Okay. First answer? Okay, so go ahead. Okay. What's the answer? Negative 75.0074. Okay? Negative 75.004. Huh? 704 newtons. Is that correct? Anyone confirm? 0? Negative 75.007. Alright? Okay. About that, huh? Okay. You all in agreement? You all happy with the answer? You happy with the way I did it? Okay? So finally, all right, finally, we do the Y. Okay. How to do the Y? Okay. Same. Okay. All right. The only difference, we cannot cancel out this gravity. Okay. M dot out, V out is rho A out, V out, multiply by V out sine 30 degrees. All right. Because we only want, okay, from up earlier here, we only want the vertical component, all right, which is going up at 70 degree. Okay. All right. Minus M dot in, V in. Actually, V in is 0. Okay, because the Y component, there's no Y component coming in. So this one is actually 0. All right. The V in is only coming in horizontally. There's no Y component in the. All right. M dot is not 0, but the V in is 0. All right. In the X component of it anyway. In the Y component of it anyway. All right. Equals F pressure. F pressure is what? Anything from the in? No, because the P in is a horizontal force. There's no Y component. So the P out is, the pressure is just minus P out, A out, sine 30 degrees. All right. It's this one here. Okay. It's this component here. And it's negative because it's pointing down. All right. P out, A out, sine 30 degrees, negative pointing down because outside acting in. Okay. Minus, okay, is equal to F gravity. What's mg again? How many? 350 newtons. All right. Okay, that's negative also, right? Because gravity points down. All right. Plus F external. So this one is rho 998. A out is what? Pi 0.15 squared over 4. V out is what? 21.3. 21.3 multiplied by 21.3 sine 30 degrees. This one is 0 equals to minus, what's P out again? 467. 600 multiplied by pi 0.15 squared over 4 sine 30 degrees minus 350 plus F external. Okay, again you punch that into a calculator, you get your answer. What's the answer? Huh? 8493.5 newtons. Okay. All right, that's the answer. Any questions? All right. Okay. All right. Before you go, I'll quiet please. All right. Since you all now got a bit freshened up because you were busy calculating away. All right. I did delay this from the last time, so I better not delay it anymore. All right. Any questions about this one? All right. So I do want to just briefly talk a little bit about lift and drag on aerodynamic on surfaces. Okay. All right. It'll be quite short, and don't worry, no calculation on this one. All right. Just a bit of explanation. All right. This would lead into the what we do the next time now. So it's actually good. All right. So okay. All right. So this is an aerofoil, more or less. Okay. All right. So we consider two streamlines. All right. One that will go over, one that will go under. Okay. There could be also many more lah. Don't worry. All right. We're not too concerned about the ones further away. Okay. All right. There will also be one poor fellow that go and crash here lah. But I'll talk more about that in the next lecture. All right. Okay. So normally, all right, we are applying the Bernoulli equation. All right. In this case, h is approximately constant. All right. We're not changing too much the height. All right. These are streamlines. Okay, now. All right. So here normally it's quite uniform. So can I say the pressure, all these points about the same? All right. So normally we call this the P infinity and V infinity. All right. So far away upstream, we have a uniform flow coming and hitting our aerofoil. All right. So remember, P plus rho V squared on 2 plus rho GH equals to constant. All right. So remember, they must match back based on this picture. If the fellow starts here and this fellow starts here, okay, they go around, they must further downstream, they must come back together. All right, cannot have a mismatch. What happens if you got mismatch? Means some extra flow has leaked in or leaked out. Okay or not? All right. This particle here, okay, further downstream where the flow settles back down again, they all come uniform again. They all must be same again. All right. Cannot have mismatch. All right. Mismatch is as if got more flow or less flow suddenly injected into this streamline. Okay or not? All right. And that cannot happen. Not in this case. All right. So if you release two particles, all right, they should come back together here because this is your control volume. All right. Okay. They cannot be. They enter the same time. They must come out the same time. They cannot be accumulated in there. All right. Okay. So if you notice, this path here is longer. Correct or not? Top path is longer. Is that right? So the velocity higher. If this is constant, if the velocity goes up, what happens to the pressure? So the pressure goes down. Here, path is shorter, so the velocity is maybe so-so or maybe even go down. Alright? So the pressure goes up. Alright? So, what you see here, you see like there's effectively a suction. Alright? Low pressure on top, high pressure below, lifting the aerofoil. That's how the aerofoil works. Okay? So if you were to draw a pressure contour, maybe you can see better ones in the textbook. Alright? I try to draw by hand. Okay? May not look very nice. here normally you have a high positive pressure acting in from the free stream. Alright? Then after that, here you have a suction on the top. Okay? Here maybe you have maybe some okay. So the here high pressure you push in, low pressure will suck. So you get a lift. Alright? So this, based on this Bernoulli principle and simple aerofoil, this is how it works. Okay? Alright? Any questions so far? Okay. So the final example, alright, same principle, but before we go, you watch football. Okay, some people watch football, some people watch tennis, some people watch cricket. Cricket got the seam here one. Alright. Okay. Some people watch baseball, but rare in this part of the world. Baseball. Okay? Alright? And it also works for a cylinder. Alright? If you have a tube, also works. Okay? But tube in 2D is also same. Alright? Okay? If they just travel through air, alright, it gets shoot straight, the streamlines will look like this. Maybe some wake and that's it. Okay? So you expect nothing much to happen. The ball more or less goes straight. Alright? It also happens in golf actually. Okay? But if you spin the ball, okay, depending which way you spin, alright, if you spin the ball, okay, then the streamline won't be like this anymore, isn't it? Okay? Alright? The fluid will get sucked over around the thing like this. Right? This is the extreme case. Okay? The fluid will follow, because the ball is spinning, on the surface where the ball is moving in the direction of the flow, it will speed up the flow. Okay now? So the V here goes up. Right? What happens when V go up? Pressure goes down. Here the opposite up. The ball, the direction is, the flow is going this way, the ball is spinning this way, so the V go down, the pressure. Alright, what do you expect the ball to do then? The ball will curve, go around that way. Alright not? So in, depending on your name, in football, what do you call it? Banana kick. In, what's the other ball this one? Tennis, what do you call? Depends. Anybody play tennis here? Alright? No. Because no tennis court here. Alright? I think can slice or top spin. Alright? Cricket, what do you call? In swing, out swing. Cricket got two types one. Because cricket very complicated. The ball can turn in the air and the ball can turn when it hits the ground also. Alright? So this one I'm talking about one turn in the air. Alright? So normally those medium placement will use this effect. Those lower one, they may not get much of this effect because ball doesn't move very fast. So they spin on the ground and all that. Alright? Golf. What's the golf called? Hook. Slice. When you get the ball to go straight in golf, what's that called? That one called miracle. Normally it doesn't happen. Okay? Baseball also very complicated. Alright? This one, it not only uses spin, but also other things which we'll talk about later. Okay? So we'll stop here. Okay? I'll see you. Oh, I've also decided, quiet please. If you want the classes like this, quiet please. No point me booking rooms here and there because it'll be all over the place and I'm not sure whether I can get it and all that. And since our class will be quite small-ish, All right, smallish. Okay, so I recommend we just do it in a fluid mechanics lab. All right, so because that one is basically I have access all the time. I don't need to book it and all that. All right, so next week this quiet please. So I repeat, this week's those doing the lab this tomorrow. All right, please bring a camera. You do flow visualization in the lab. Next week for the Monday, Tuesday, and Wednesday slot, I have to inform my tutors. All right, you can come in the go straight to the fluid mechanics lab. We'll do it in there. All right. All right, and those doing the Wednesday, the normal slot, we'll do it in the normal, since we already have the classroom. All right, classroom. Okay, that saves me booking room and moving all over the campus and so on. Wait, off recording first.